The goal for this video is to come up with a way of computing the exact area of a region in the plane, rather than simply an approximation. So let me outline the main idea for this. We know that Riemann sums can be used to approximate the signed area of a region, and we know that the more rectangles are used, the better the approximation. So we'd like to be able to somehow use infinitely many rectangles, and then we would have the exact area. But there's a problem with this. If we had infinitely many rectangles genuinely, then they would each have zero width and therefore zero area, and in fact the idea of adding up infinitely many areas is sort of problematic. But there is a way around this. What we can do is simply compute the Riemann sum using n rectangles, leaving the number of rectangles a varying parameter, which we can then let go to infinity. So what this really means is that we're computing a sequence of approximations which we then let approach this exact value. So how do we do this? If I'm trying to form the generic Riemann sum of a certain function on a certain interval, what we do is we're dividing this interval from a to b into n subintervals of length, we're calling it delta x, and that's the length of the interval, b minus a, divided by the number of rectangles. And so this is what it would look like in general. We're dividing it into n subintervals, each of length delta x. Now in each subinterval, we're selecting a sample point, x1 star, x2 star, up through xn star. In each subinterval, there's some x star. And these are going to depend on which type of Riemann sum we use. However, for this technique, I use only right endpoint Riemann sums because they're a little easier to express formulaically. For instance, if we use right Riemann sum, then x sub I star is just a plus I delta x. Let me try to convince you of that. x1 star should be the right endpoint of the first subinterval. That would be a plus delta x. And this formula agrees with that. If I let I equal 1, then that's a plus delta x. And the last one, x sub n star, should be the right endpoint of this last subinterval, which is b. So if I plug in n for I, then I notice with this second formula that I equals n would cancel with this n, and I'd be left with a plus b minus a, which is equal to b. So that is correct. Okay, now what is the corresponding Riemann sum? Well, the heights of the rectangles will be the function value at our sample points, f of x1 star, f of x2 star, and so on. And so the corresponding Riemann sum is f of x1 star delta x plus f of x2 star delta x, and so on up to f of xn star delta x, which we can compactly write using sigma notation. And now that we've done this, we can give the exact answer to our area problem. Our approximation using n rectangles was this Riemann sum, and now we simply let n approach infinity after we've computed that approximation. Let me show you how this works in practice. So we're going to compute the exact area of this region under the parabola y equals x squared from 0 to 2. Now in this case, the left endpoint was 0 and the right endpoint was 2. A and b are 2 and 0. So delta x is just 2 over n. And again, in this business, when we're taking n approaching infinity, it doesn't matter which type of Riemann sum we choose. Left, right, or midpoint makes no difference. So I use the right endpoint Riemann sum for this because the formulas for the sample points become relatively simple. A plus I delta x. Okay, in this case IA is 0, delta x was 2 over n, so the sample point x sub I star is equal to 2i over n. And so we can compute the area now using our limit of Riemann sums definition. So first, let's see, what is f of x sub I star? Well, x sub I star is 2i over n, and our function was just y equals x squared, so we're squaring our sample point, times delta x, which we've already computed was 2 over n. Alright, let's simplify this. I see that we have in the numerator 2 squared times 2, that's 8, and in the denominator we have n squared times n, that's n cubed. So 8 over n cubed is a constant multiple of what's inside this sum here, so we can pull that out. And I'm left with just I squared. Alright, but we have a formula for the sum of I squared from 1 to n that was shown in the video on sigma notation. and it was n times n plus 1 times 2n plus 1 all over 6. Okay, let's simplify this. I can cancel a 2 on the top and bottom. I can also cancel an n, so let's go ahead and do that. This becomes a 4, that's a 3, and this n is gone, and this is now n squared. And I notice that I can split this up as follows. I'm doing this just so that I can easily compute this limit. The degree of the top and the bottom is the same in both cases, and so it's just leading coefficient divided by leading coefficient in either case. So that's 4/3 times 2, which is 8/3, which is the exact area of the region we were looking for. Now I want to point out that this was a rather lengthy and difficult computation for such a nice function as y equals x squared. In section 5.4 we are going to learn a much easier method for computing these definite integrals, which involves the use of indefinite integrals. And it's this connection between the area problem and indefinite integrals which will motivate us to use the following notation. We use the notation integral from a to b of f of x dx to denote the signed area under the graph of f of x from x equals a to x equals b. So in other words, this symbol here, the integral from a to b of f of x dx, is equal to this expression that we've just computed. So this expression, the integral from a to b, is called the definite integral of the function f of x from a to b, and a and b are called the limits of integration. And it's important that we don't mix this up with the indefinite integral, which had no limits of integration. Now, loosely speaking, to try to explain this notation, once we take this limit as n approaches infinity, you can think of this sum turning into an integral, and you can think of this delta x as turning into this dx. The idea traditionally was that instead of having a finite number of rectangles, what you have is sort of an infinite number of rectangles of infinitesimal width. I already discussed that that didn't make precise sense, but that is traditionally how we think of these things. Now in section 5.4 we'll see the connection between the definite and indefinite integrals, but for now at least you should understand that the definite integral is a number. It's the area, the signed area, of some region, while the indefinite integral is a family of curves, all of the antiderivatives of the function f. Okay, let's see an example of computing a definite integral. So we're going to compute this definite integral by identifying the curve y equals square root 9 minus x squared as a familiar geometric shape. Okay, so the curve that I've represented here is, I claim, the upper half of the circle with radius 3 centered at the origin. To see this, just note that if we square both sides and then adds x squared to both sides, then we get x squared plus y squared equals 3 squared. And that's exactly the equation of a circle with radius 3 centered at the origin. But on the other hand, this square root expression can only be non-negative if it's defined at all, and therefore the bottom half of the circle is not going to be part of the graph. And therefore, this integral that we're meant to compute is simply the area of the following shaded region, from 0 to 3 of the top half of the circle with radius 3 centered at the origin. Alright, but this is an easy area to compute once we know the area of a circle. Pi r squared, it's just going to be 1/4 of that. So let's do that. Pi 3 squared over 4 is 9 pi over 4, and that's the exact area of this region, and that is the exact value of this definite integral. I do want to admit to you that this method is almost never useful. For instance, this method would not tell us the integral from 1 to 3 of this same function. Right? I mean, from 1 to 3, that would be the area under this curve from this vertical line to the right. And that's not easily recognizable as some proportion of the area of the circle. But I wanted to give this example because it does emphasize the concept that this definite integral is merely an area, rather than a family of curves like the indefinite integral was. Okay, we have properties of definite integrals which allow us to compute. The constant multiple and the sum rule are both valid, and they're used exactly the same way as with indefinite integrals. But we also have a few other properties. This first property is really more of a definition, if you want. What it's saying is if we switch the upper and lower limits of integration, then that changes the integral by a sign. We can switch the limits of integration at the cost of introducing a minus sign. We also have this property, which is rather obvious once we interpret this as area. The area under the curve from A to B plus the area under the curve from B to C is equal to the area under the curve from A to C, which is rather obvious. Also, if the graph of f of x lies below the graph of g of x, then the area under the curve of f is less than or equal to the area under the curve of g. This is, again, totally obvious once we've interpreted this as area. Okay, let's compute some examples using these properties. So using first the sum rule and the constant multiple rule, I can break this into three separate integrals, just as we did for indefinite integrals. But now I'm going to focus on each of these integrals separately. This first one we already computed. That was 8/3. That was the first example in this video. The second and third integrals I claim are easy to compute geometrically as well. This second integral will be the area of a particular triangular region, and this integral here is the area of a rectangular region, which I can now show you. Oh, well, of course, we could simplify this. 8 minus 8 plus 2 is 2. So let's see what areas these two integrals represented. The integral from 0 to 2 of just x is just the area of this triangle, and that's going to be given by 1/2 base times height. And the integral from 0 to 2 of just 1 dx is the area of this rectangle, which is just 2 times 1. Okay, let's see some more examples. Since we already know that the integral from 0 to 2 of x squared is 8/3, it follows that the integral from 2 to 0 of x squared is negative 8/3. And here's another example. Let's say we have a piecewise defined function. This function is given by two different formulas based on which interval you're looking at. So if we want to compute a definite integral, which involves pieces of both of these, it's natural to try to split this up into two integrals. One from the interval from -4 to 0, plus another integral from 0 to 6. The benefit of doing this is that on the interval from -4 to 0, we can replace f with this formula, 3x minus 1, and on the interval from 0 to 6, we can replace f with this formula here, cosine 5x. And so now we have two more concrete looking integrals which we could try to compute separately. I'm not going to finish this example, however, because we won't actually have the tools to compute this integral, cosine 5x, until section 5.5. Okay, to recap, the definite integral is the signed area under the graph of f of x from x equals a to x equals b. And the definite integral can be understood as a limit of Riemann sums, which explains our strange notation for it. And in the next video, I plan to give you this connection between the indefinite integral and the definite integral, and therefore we'll have a better way to compute these definite integrals in the future. But before we do that, I'd like you to please try your hand at answering these questions, and I will see you in the next video.